In the last class, we were talking about basic behavioral modeling. We said that objects interact by passing messages, and an interaction is a behavior comprising a set of messages which are exchanged among a set of objects with the objective of accomplishing some specific task. We use interactions to model the dynamic aspect of collaborations. So we were looking at ways, the dynamic aspects of UML, how the flow of control encompassing simple sequential threads as well as complex threads are represented. And we said that interaction is modeled in two ways, either by emphasizing the time ordering of messages or emphasizing the structure of messages in context of the structural organization of the system. And the first of these is captured by sequence diagrams, the second by collaboration diagrams. And then we talked about use cases. A use case is a description of a set of sequences of action, including variants that a system performs to yield an observable result of a value to an actor of the system. And we looked at some simple use case diagram. This is an example of a use case diagram where there are four actors: customer, salesperson, shipping clerk, and supervisor. And this diagram uses four use cases: check status, place order, fill orders, establish credit, and we show the links between the use cases and the different actors. We also went into details of some use cases. An actor is defined to be someone or something that interacts with the system. And typically the actors are the users of the system. They can also be other entities, including other computer systems, and they are abstract, and actors can be active or passive. Today we will finish talking about use cases, and then we will discuss the different interaction diagrams, the collaboration and the sequence diagrams, and then go on to activity diagrams. In order to use a use case, first it is necessary to establish the context of the system. And how is the context of the system identified? So first you identify the actors that participate in the system. The actors surrounding the system have to be identified. And then you look at each actor and find out the behavior each expects or requires the system to perform. These common behaviors which the actors expect or require the system to perform are known as use cases. So each behavior is a use case. Then the common behaviors of the system we have to see if they can be factored into other use cases. Factor the common behaviors into new use cases. And then factor variant behavior by new cases which extend some of the use cases. So after the various use cases of the system have been identified, these use cases, the actors, and the relationships between them are captured in a use case diagram for the system. Then we may need to add certain notes to these use cases in the use case diagrams explaining the function of its use case. Next comes the question of realizing use cases. So use cases are realized by, as you have seen, by use case diagrams. And the system requirements, as we have said, is collected as a set of use cases. And after the use case diagram is constructed, this forms the key source for further modeling. And we also have said that use cases are realized by a collaboration of objects in the system. Use case diagrams are realized by a collaboration of objects. So the next step, we use collaboration diagrams and sequence diagrams to show how objects collaborate to constitute the use case. Next, we may draw activity diagrams to show the steps in the use cases. So this is how use cases are realized in the system. So by modeling use cases, we can derive an iterative development process. All the use cases, the final use cases, are not always collected in one go. So some use cases are collected and it is tested whether the entire system is modeled using these use cases. And maybe other use cases are collected, and this can form the basis of iterative software development. Also, use cases can be used to design validation tests. So after the system is implemented or designed, you can test whether each use case is satisfied by the system. So this forms the basis for designing validation tests using use cases. Next, we will take up the interaction diagrams. And as we have said, there are two kinds of interaction diagrams, sequence diagrams and collaboration diagrams. And they show an interaction which consists of a sequence of objects, a sequence of messages, and their relationships, including the messages that are dispatched between the objects. Interaction diagrams, they show an interaction consisting of a sequence of objects and their relationships including messages dispatched among them. And as we have said earlier, there are two kinds of interaction diagram. Number one is sequence diagram. Sequence diagrams are used when we want to emphasize the time ordering of messages. And alternately, we can use collaboration diagrams. Collaboration diagrams emphasize the structural organization of objects. Of objects that send and receive the messages. Next, we will have a look into how these diagrams are constructed and look at some examples of some of these diagrams. So first, let us see what are the steps taken to construct these interaction or collaboration diagrams. So first, let us come to sequence diagrams. And let us look at the steps in constructing the sequence diagrams. So first, we have to place the objects that participate in the interaction at the top of your diagram. So you identify the actors or the objects in the interaction and then place them along the x-axis at the top of your diagram. For example, suppose let us try to model a system which consists of a client and an ODBC proxy. So the two objects here are a client. We want a particular object, a C of type client, and we have P is an instance of an ODBC proxy. And we want to model a transaction between this client and this proxy server. So along this axis, we are showing the objects. So objects initiating the interaction are shown at the left of the diagram, and the other objects occur to the right. And increasingly more subordinate objects occur more towards the right of the diagram. Now, in order to model this interaction between the client and the ODBC proxy, another object is constructed which is called the transaction, which comes into existence at the start of the interaction. Now we have to, in this diagram, we also show the messages that are messages that are passed from object to object, and we also have to show the lifeline of an object. That is, we have to specify the time during which an object is active. And the lifeline is plotted along the y-axis from top to bottom, and the messages are shown horizontally from one object to another object. Now first, let us try to draw the lifeline of the client object. The client object starts from this time. So along this axis, we are plotting the time. And after the client object, when this object C comes into being, sometime after that, it creates a transaction object. So we have an instance of the transaction object. So let us say this is an anonymous object. And this transaction object is created by the client sending a message create to the transaction object. And it is then that the transaction object starts. Now we have the ODBC proxy server here, and on being created, the transaction object sends a message set values to the ODBC proxy server. And in response to this, the ODBC proxy server does some computation. Now this denotes the lifeline of the system, the time from which this object is alive, the object comes into being. And we denote by rectangles those times which are of interest to us, when some important activity is going on. So this ODBC proxy does some computation after receiving this message, and this particular time we are representing by this rectangle. Subsequently, this transaction process sends another message to the ODBC proxy server. Let's say that the message is set values, another set values message, and then some other computation takes place. And the ODBC proxy server continues computation. So after this particular message has been sent by the transaction object has finished its function, and the transaction object sends a message to client saying that the object is committed. Following this, this is an end of the interesting part of the transaction object, and since the transaction object is no longer required, the client may send a message destroy to the transaction object. Following which the transaction object is killed. It ceases to be in existence. And the client and ODBC proxy, which are persistent objects in the system, continue to be there, whereas the transaction object, which is a transient object, its lifetime varies from here to this point, whereas the ODBC proxy and the client, their lifetime continues further. So let us write down the steps corresponding to the construction of this sequence diagram. To construction of this sequence diagram, right? So we first place the objects that participate in the interaction at the top of the diagram. Along the x-axis. The object initiating the interaction is placed at the left. Increasingly more subordinate objects are placed to the right of it. Then we place the messages that these objects send and receive along the y-axis in order of increasing time from top to bottom. And there are two interesting features in sequence diagrams which we will later see is not present in interaction diagrams. One is this lifeline. It represents the existence of an object over a period of time. So lifeline represents the existence of an object over a period of time, and secondly we have focus of control. So focus of control is represented by a tall rectangle which shows the period of time during which an object is performing an action of interest to us. Now we will look at collaboration diagrams in a little more detail and then come back talk about a little more about interaction diagrams. Collaboration diagrams, as we have said earlier, emphasize the structure of the objects that participate in an interaction. And let us look at the steps required in constructing a collaboration diagrams, and then we will see an example of a collaboration diagram. This is a let us try to model the same system that we did earlier with an interaction diagram with the collaboration diagram. The different objects that take place in the interaction are the client, the ODBC proxy, and the transaction. So in this collaboration diagram, we have to construct a graph, and the objects that take place in the interaction are placed as the vertices of the graph. Then we have to render the links that connect the objects. So this client is connected with transaction and the ODBC proxy with the transaction 2, and these links form the arcs of the graph. And then we have to add on the links with the messages that flow between one object, between the sender object and the receiver object. So what are the messages in this system? The messages sent by client to the transaction are, there are three messages: create message, then set actions message, and then destroy message. And these numbers 1, 2, and 3 denote the times of the messages. The first, the create message is sent, then the set actions message is sent, and then the destroy message is sent. And we also show the direction of these messages. And then let us look at the messages sent between transaction and ODBC. There are again two messages. One is the set values D, another is set values A. And then these particular messages are sent during this message number 2 here, during this time 2 here. So we nest the time and write these times as 2.1 and 2.2. And then we may also put some adornments on these particular links, like this is a local, this is global. So these things are called path stereotypes. These two are links. These three are objects. And these are messages. This is a transient object. There are two distinguishing features in collaboration diagrams. Number one is path. A path indicates how one object is linked to another object. And the second thing of importance is the sequence number. and the sequence number in the collaboration diagrams show the time ordering of the different messages. You must note that semantic diagrams and collaboration diagrams are actually semantically equivalent, and so you may represent any one of these diagrams, and you can also convert from one of the diagrams to another form. So now let us look at a little more detail into interaction diagrams, and first let us take up sequence diagrams and let us show how we model the flow of control by time ordering. So the step 1 is to set the context for the interaction. So for this, you have to identify the systems, the subsystems, the classes, and the objects that take part in this interaction. Secondly, you have to identify the objects that play a role in this interaction. So these objects are laid out in the sequence diagram from left to right. The third objective is to set the lifeline of each object. The fourth task is to look at the messages. So starting with the message which initiates the interaction, we lay out each subsequent message from top to bottom between the lifelines. And two other steps that we perform are, we adorn each object's lifeline with the focus of control, show the focus of control on the lifeline, and finally we adorn each message with a timing mark. And attach suitable constraints if required. So first we set the context of the interaction by looking at the systems, the subsystems, the classes, the operations that take part in it. Then we identify the objects that play a role in the interaction and lay them out in the sequence diagram from left to right. We set the lifeline for each object. Fourthly, starting with the message which initiates the interaction, we lay out each subsequent message from top to bottom between the lifelines. And finally, we put two adornments in the diagram. We identify the focus of control in the lifeline of the various objects, and then we put timing marks on messages to indicate their time ordering, and we may also put suitable time or space constraints in the diagram. So let us illustrate this by looking at another sequence diagram. So this sequence diagram is for a system which involves a telephone call between a caller S and a caller S and a caller R. So these are the two objects, caller S and caller R, and there is also a switch object which makes this telephone call feasible. So after we have identified these three objects, we draw the lifeline of these objects, and then we find out the set of messages which are exchanged between the objects in the order of the time in which the messages are exchanged. So first message, lift receiver, is between caller and switch, and then from switch to caller we have set dial tone. Then from caller to switch we have dial digit D, which is a dialing message. And then there is some activity which involves a self message call from switch to itself, which is route calls. So route calls SN. So after this route call has finished, the switch sends a create message to create another new object, a conversation object. So C is a conversation object which is created by the switch after the route calls. And then the conversation object comes into existence, and the conversation object sends the ring message to the caller R. The caller R sends the lift receiver message, does lift receiver, and the message is sent to the conversation object. Conversation object sends connect RS to the switch, and the conversation object now sends connect S to the caller, connect R to the caller R, and the message connect S to the caller S. And so this is the total system. So this connect messages are those messages by which caller S and R may exchange information after both are connected. So this involves four objects: caller S, conversation C, caller R, and an anonymous switch object. And these are the messages that take place between the objects. Next, we look at how in collaboration diagrams we model flow of control. So first we set the context for the interaction. Second, identify the objects. That play a role in the interaction. And lay them down as vertices in the graph. And by laying them down in vertices, place the more important objects in the center of the graph. Thirdly, you specify the links among these objects. And along this, such that messages may pass along these links. And so this involves laying out the association link first. The association links represent structural connections, and secondly, then you lay out the other links. And maybe you adorn them with suitable path stereotypes. Following this, you start with the message that initiates the interaction. Starting with the message initiating the interaction. Attach each subsequent message to the appropriate link and set its sequence number. And finally, you attach time and space constraints if necessary. So let us see an example of an interaction diagram, of a collaboration diagram. So we have this process system represents the registration of students in a school. R is a registrar agent, is an object of type registrar agent. This is an object of type school. S is an object of type student. S is object of type student whose registered attribute is true. This student registered attribute is false. C1 is an object of type course. C2 is another object of type course. So the first message is between the registrar agent and the student. Registrar agent creates the student. The second message is between registrar agent to school. The message is add students, which has the sequence number 2. Then the third message is from registrar agent to student, and the message is register. So sequence number 3 is register. 3.1 is get schedule, which is a message sent by student to itself. 3.2 is add S, which is a message sent from student to course. And 3.3 is another add S sent by student to another course, C2. 3.4 is a message sent from student to another instance of student, and the stereotype for this message is becomes. So student whose registered status is false becomes student with registered equal to true following this link. Next, so now we have looked at the two different types of interaction diagrams for modeling interactions, sequence diagram and collaboration diagram. Next, we will have a look at activity diagrams. So activity diagrams are also used to model the dynamic behavior of the system. So activity diagram involves modeling of sequential and possibly concurrent steps in a computational processes. The formal definition of an activity diagram is this: an activity diagram is essentially a flowchart showing the flow of control from activity to activity. Activity diagrams can be used to model the workflow as well as program details and activity diagrams in UML are also related to state charts. So state chart shows the flow of control from state to state, while activity diagrams show the flow of control from activity to activity. Now let us first look at the syntax of activity diagrams, look at the different symbols, and then we will have a look at some example activity diagram. So activity diagram consists of two types of states: action states and activity states. So activity states are represented like this. And then we have action states, which are represented like this. Then input events are represented by an arrow. output event are represented by another type of arrow. And then there are some other things, for example, object flow state, which is represented in a rectangular box with name, colon, type of object and the status of the object underlined. Besides this, there are some other types of links in activity diagram. This link denotes fork or join. This link denotes transition. This sort of dashed link denotes control flow, flow of control. And the diamond represents a branch or a march. An activity state, which is denoted by like this, may consist of many other activities. So an activity state is not atomic and it has some duration and it may be interrupted during that duration. Whereas an action state is an atomic state which consists of an atomic action. So this state, activity state, may contain other activities, can be decomposed into other activities. And action state is an atomic state. An action state can be used to represent the evaluation of some expression, sending of a signal to an object, calling an operation on an object, etc., which are atomic events and which may not be further decomposed into other activities. The object flow state it shows the value of an object which is created or used in an activity state. Branching and marching is denoted like this. Branching is denoted by a diamond. Suppose you have an activity state here, S, and there is an event when the branching takes place. You can attach the condition with the different branches. Suppose under condition 1, the system follows this branch. Under condition 2, the system follows this branch. And here it goes to activity state S2, here it goes to activity state S1. And here they get marched. Sometimes you also attach an else with one of the branches, so which denotes the default branch to follow. This is how branching and marching takes place. And then fork and join are represented like this. Suppose you have a state S. So this is where forking can take place, and you may fork to two different states, Q1 and Q2. And a matching line shows a join. So this thick line denotes a fork, this thick line denotes a join, and then the system may continue execution. Now let us see how signal send and receive is modeled. A signal send and receive may be modeled. The model is shown in this example. this is an action state consisting of enter credit card data, this is a state corresponding to await authorization, so if the amount is less than 250, we come directly here. Directly, when you enter credit card data, you directly charge card. If amount is greater than 250, then you send a signal. Send credit card card center dot request. You send a signal and then awaits the authorization, and after that you charge the card. So we will look at an example activity diagram in the next class and then go over to architectural modeling and wrap up this discussion on UML. Thank you.